lahko začnemo. Good day. Matjaž will today present you the new equipment, the Imperial diffractometer. And after that, if you want, you can also go with him to the K9 for a demonstration. Please, Matjaž.
Hello everybody. So in today's talk I will explain what are all the applications which can be used with our new cutting-edge Imperial diffractometer, which was installed and at our department at K9. It was bought by the Center of Excellence, and actually it is meant for also all of you which have certain demands or requests within your PhD research. So this is the outline of the presentation. I'll explain all the analysis which can be carried out, not all of them, but most important analysis. So first Bragg-Montano, reflection on ambient transmission, then small angle X-ray scattering, racing incident, XRD, X-ray reflectometry, high resolution, XRD in-plane, and to the applications. So at the beginning there is one thing which needs to be emphasized. All these applications are possible just because of the so-called prefix. Prefix is a patented way of the analytical company which enables you to switch all the optics and the sample stages within several minutes without any subsequent realignment of the goniometer. So this is really nice. So let's say optics can be exchanged within 5 to 10 minutes, while the sample stage is like half an hour or even less, maybe 20 minutes. So this is very beautiful thing because with the old diffractometers, when you change optical configuration, then you had to be very experienced that a proper realignment of the optics was done. So actually this is a short overview of configurations which can be done on the very same diffractometer. So let's say, so the diffractometer is a big box, and then inside the box we have goniometer. These are these two arms which move. So this is the so-called omega, this is the so-called 2 theta. So omega has X-ray tube, and then here we have a number of slits, and I'll explain which slits do we have. Here we have a sample which is mounted on a sample stages. So here exactly we have a spinner, so it's meant for powders, and then this powder rotate while the sample is being recorded. And then we have a diffracted part. Here we have different slits, monochromators, etc. And detector. This is again one very important part. So with the goniometer, you change these two arms in a certain way so that you bring your crystal into the diffraction condition. There are other options of this goniometer. So this is the so-called vertical version, which is meant for smaller samples. But you can also have a horizontal diffractometer, which is then just tilted for 90 degrees like this, and then these two arms go like this. Why we use vertical and why we use horizontal diffractometers? Horizontals are used for larger wafers, let's say above 6 inch, because in these cases both optics has to be further away, and then this is getting heavier and heavier, and as the mass is bigger, then it's getting very hard to very precisely control the exact angle of the arm. So when you put those two arms on the back, then actually there is much less force because then you rotate them in plane. Yeah? Okay, so this is let's say configuration for standard Bragg-Montano. setup. Here we have X-ray source, and the beam is going out, which is divergent. And then this divergence is corrected using, let's say here, PDS and some mask, as well as solar slits. And on the diffracted side, we have PAS. This is programmable anti-scatter slits. But I'll tell you later on all the details about that. Okay, so this is, let's say, one configuration, and then we decide to do, let's say, texture analysis. So we change the fixture to the cradle. So this is the spinner. We go to the cradle, and then with the cradle we can correctly position the sample. Then we can do also non-ambient measurements. So here is a Anton Paar high temperature furnace. So this is, let's say, a little bit more time consuming to be replaced, like half an hour, and so on. But actually, this can be exchanged very quickly, and no realignment is needed. So this is something that Panalytical is really proud of. Okay, so Bragg-Brentano. Why we do Bragg-Brentano measurements? This is actually just reasons which are listed. Normally, we want to, with the X-ray analysis, we want to figure out which phases are present in the material that is being analyzed. And with this kind of analysis, we can go like 20 micrometers depth into the material. We analyze crystal planes which are parallel with the surfaces, and this method, this application is most suitable for polycrystalline samples. So we analyze which phases do we have, what is the symmetry of this phase, what is the size and their strain. We can then refine exactly unicell parameters and do some quantitative analysis. In most of the cases that will be presented today, Bragg-Brentano is the law which determines what will be recorded on the detector side. So the diffraction is governed by the Bragg's law. It's a very simple law. It relates wavelength of the X-ray, which in our case is a copper radiation with the wavelength of about 1.54 angstrom. And for a certain d-spacing, which is a distance between crystal planes in our materials, and at a certain wavelength, then we know at exactly which angle we have to shine on our material that we get a constructive interference out from the crystal. So this angle is just determined by the law. Okay, another important issue is Ewald sphere. Again, using the same wavelength, we can determine the radius of Ewald sphere. Here is the origin of our material, and if we change the angle of this material, then the Ewald sphere is moving. And here we have a reciprocal lattice points, and in case Ewald sphere intersects with a reciprocal space bond, we have a condition for the diffraction, and actually at that condition we get then a signal in the detector. Okay, so this is actually important for most of the application, but we also have some scattering and reflectivity applications, but this will be then described later on. And in these applications, the Bragg law is not ruling the process. So in Bragg-Brentano measurements, we actually deal with the parafocusing geometry. So this is the definition of the Bragg-Brentano. So we have the source, and then the beam which is divergent. So with the certain slits, we limit the divergence in this direction. So this is the so-called divergent slit, which can be programmable or fixed. But we also have to correct the divergence in this side. So we do this with mask and solar slits. And then the beam goes on the crystal. So the central line, let's say, goes on this crystal, which is perfectly aligned with the substrate, with the surface, and then you have a diffraction condition, and then the signal goes to the detector. But due to the divergence, we also shine on another crystals, and this angle is then different than this one. So basically, if we shine on the crystal with a certain orientation which is different than this crystal, we can also get a diffraction condition. So basically, due to different angles, more crystals or let's say can fulfill Bragg law, and then as a result, more signal is collected in the detector. Yeah, basically, if the beam is parallel, then for polycrystalline sample, we would get a less intensity in the detector. Okay, so this is the configuration, the image of our device. Here is X-ray source. Here we have solar slit, and this is a PDS. PDS so corrects the divergence in vertical direction, solar slit, and mask on the other side in horizontal direction. Then we have also anti-scatter slit, which eliminates scattering effects from the air. Then here is a sample stage. So this is a spinner, which can be also the cradle for different positioning of X, Y, Z, and also phi, which is rotation in chi, which all this direction enables you to orient crystal exactly in the space with respect to the goniometer. And then on the diffracted part, here we have, let's say for configuration for Bragg-Montano, we have normally pass, which is programmable anti-scatter slit. This is again, as we have here, anti-scatter slit for elimination of scattering of air. We also need to have a similar slit on the diffracted side. So in this configuration, we have a monochromator, which eliminates fluorescence. This is exactly shown here. This is this monochromator. It's a 1D monochromator. It's a very nice one, but I don't want to go into details of that monochromator. Then we have a nickel foil in order to remove beta radiation, and then detector, which will also be explained later on. So this is typical configuration. These are all the components which can be exchanged. And I'll say a few words about the hybrid on the detector side now. Okay, maybe one more thing which is very nice with our configuration. We have an automatic sample exchanger. So basically you can put like up to 45 samples in a queue, and they can be collected, let's say, during the weekend. So they're automatically grabbed by this arm and put into the spinner. Okay, so I said hybrid monochromator. This is a solid piece which is presented here. It is constructed of a mirror with a parabolic shape, and this mirror is changing divergent beam into the parallel beam. Yeah? Why this is required? This is required for high resolution measurements on a one peak. Yeah? If you do Razavillit refinement on the whole spectrum, then this is not a good optics. We need to have divergent beam. But if you do high resolution measurement on one peak, then we decide for this kind of geometry. And then next to the mirror we have a crystal. This is a so-called two-bounce crystal. So the X-ray is bounced twice on this crystal, and in this way we get only K alpha 1 radiation out of it. Why this is important? Normally, if we know what exactly our material looks like, we can work with both radiation, K alpha 1 and K alpha 2. Why we decide for both radiation? Because intensity is much higher, as in case we remove one of these two. So basically, what we get out of the tube is a copper radiation, and this radiation has a certain distribution of wavelengths, and K alpha 1 and K alpha 2 are very close to each other. So if you want to remove one, then the intensity of the second one is pretty much decreased. So normally K alpha 2 is twice the value of K alpha 1, and if you decrease it, then you strongly affect the intensity. So only in cases when you would like to study the symmetry of your sample or a new compound, then you decide, let's say, for K alpha 1, or when you do high resolution measurements. Let's say this is the example of both radiations. So here we have, let's say, like 1, 2, 3, 4, 5 peaks for K alpha 1 and 2. And actually when we go to k alpha 1, we can see that actually this one and this one is removed, while this one is decreased for half to the half of the value. So basically, why it is so? Because this is producing another peak for k alpha 2, and then actually the material has also a peak on this position. So basically, this is doubled, yeah? And this is just k alpha 2. Yeah? So if you want to see the symmetry of your sample, then it can be pretty much complicated if you work with both wavelengths. Yeah? Okay. Then detector. A few words about the detector. It's a solid state detector with number of pixels which are very nicely arranged in two dimensions actually. And actually, what you can do is to integrate signals from this pixel in different way. So you can integrate all of them, and then you work with the so-called zero-D detector. This is also called point detector. You can integrate all the signal in a line, yeah? And then you get a 1D detector or a line detector. Or you can work just in the same way as pixel arts are originally fabricated. So in this case, you work with the 2D or area detector. So in most of the Bragg-Brentano applications, we use a detector in 1D mode. Why is this so? This is explained in this image. So we have a divergent beam, and this beam shines on a polycrystalline sample, and we get diffraction at different angles. And basically, this line detector works as a series of detectors. So actually, each line acts as an individual detector. So we have like 256 detectors at the same time. So that means that the acquisition time is divided with 256 according to, let's say, a normal zero-D detector. And then you can get already a nice spectra after 2 minutes, yeah? In the range, 2 theta range from 10 to 60, yeah? I mean, something for the routine verification of, let's say, of the synthesis between two solids, yeah? Okay. So this is then the typical pattern that you get out of the measurements. So we have 2 theta values, and you have different intensities. You have some peaks, and based on these peaks, you can say what is your symmetry, what is the crystal structure at the first place, what is the symmetry of that crystal structure, whether there are secondary phases present, or let's say if you have 50-50, what is the exact ratio between them, and so on. And then you can do also, let's say, size and strain, and so on. Okay. Now it's still Bragg-Brentano, but not reflection, but non-ambient measurement. So this is, let's say, one nice application that we can do. So we work with the detector in 1D mode. So that means that we can cover a certain range of 2 theta values, and then this is, let's say, presented in this range. Yeah? So we don't change the 2 theta value. We don't change the collimator, but we keep the detector at a certain position. But because of the number of lines that we have, we can record a certain spectra of 2 theta values. And then at one temperature, what we do, we just take a snapshot. We change the temperature and then taking a picture. And then what we can see that, according to the material that we have, at a certain temperature we have, let's say, some phase transitions, and this can be very nicely studied. So you don't need to change arms of the collimator, but you just then change the temperature and make a move, yeah, actually. So this is very nice because it can be quite a quick measurement, because, let's say, in the past, this temperature-dependent measurement were really time-consuming, yeah? But this is now getting much faster. So there are different stages which can be bought nowadays on the market. we let's say bought the one which is in the circle. So these are Anton Paar cameras. The one we have can go up to 1200 degrees C. We can go even higher, but then you have a certain drawbacks, certain benefits. Of course, we decided for this one because you don't contaminate your chamber as much as in case you work with the chamber that go higher, because in that chambers you have a direct contact of the heating element with your powders, and this is then causing a lot of problems for let's say for an analysis which can be done, let's say, after analysis of compounds like bismuth, potassium, sodium, which evaporate a lot, and then this will contaminate your environment over there. Okay, you can also decide for high pressure chambers or for chambers with high humidity. But let's say this is one chamber which was also bought at Krka in Novo Mesto. So they also bought Empyrean, but with high humidity chambers. Then another thing that we have is a cryostat, which can be replaced with high temperature chamber. So with the cryostat we can go from 11 K up to a temperature slightly above the room temperature. So this is really nice. So if there are, let's say, some phase transition which might be, let's say, interesting for people that work with superconductive materials, we can study them as well in this device. So we can go from 11 K up to 1200 degrees C. Yeah, so very broad temperature range. Yeah, and this is a closed cryostat. That means that we don't lose helium. Yeah. Okay. Then another application, still Bragg-Brentano, is transmission. Transmission is not very often used, but let's say it can be used in some materials that are more or less transparent, and in this case you can get, let's say, higher intensity on the peaks, and let's say at lower 2 theta value, smaller background, yeah, which is presented here. So if you do a reflection measurement, you have here a lot of signal, but if you do transmission, the signal is decreased, yeah, But in the community we are in, transmission XRD is not really used. Yeah? So this is, let's say, this is done on cacao, which has a high transmittance. But actually, the geometry which is used for the transmission XRD measurements is also used for SEX measurement. This is small angle X-ray scattering measurements. So basically, this is the reason why we also are interested in the geometry itself. In this geometry, we can analyze particle size distribution from 1 to 100 nanometer. We can analyze their shape and specific area. So this is not a diffraction event, this is a scattering event. So it's just like there are also many particle size analyzers at the institute. So they use a laser light and they shine on the suspension, and then according to the size and the shape that you see the scattering. Yeah? Okay, so what can be analyzed? Nanopowder, liquid scattering, liquid dispersions, nanocomposites, porous materials. And as I said, it can be amorphous or crystalline, since we don't have a diffraction requirement. So these are normally the density, the results. So with the change of 2 theta, you have a variation of intensity, and based on some models which are proposed, and for your materials, you can see what is the volume distribution of the material according to different radius of the particles that are inside. So basically, you can see, let's say, for these particles, you have a narrow size distribution, while for these particles, you have quite a broad particle size distribution. This is not as accurate as real. This is so-called easy SAG, so it's not as accurate as real SAGs. Then the second application, so now we are getting more and more closer to the thin films. That was more or less for powders and for nanopowders, and now we're getting to the thin film investigation. So this is the first one, which will be explained now, is Gray-Zinc incidence XRD. It is meant for analysis of polycrystalline thin films. Why we do it? Because we would like to have a nice information of the composition with the changes of depth. In this way we enhance the diffracted signal from the top layers, and we remove we decrease the intensity of the substrate. So again, very similar thing as for Bragg-Brentano phase ID, size strain, lattice refinement, and quantitative analysis. So this is the geometry. So what we do, we put omega at a certain value, which is then fixed, and then this omega is very small, normally like 0.5 degree. And because it is a small, then your path of X-ray through the film is long. If you shine at higher angles, then the distance is short. If you go at very small angle, then the distance is long. And then based on longer distance, you get more signal into the detector. And then what you change is the 2 theta. So let's say here is one example. So this is the incidence angle. It was changed from 0.3 to 2 degree, and then at the very small angle you get the top layer. And then you increase the angle, let's say to 0.6, you get information about the layer underneath zinc. And then you further increase to 2, and you get even more information from the bottom, from the material below. And this is then this compound. So this can be like depth resolved phase analysis. Okay, here is one comparison, Bragg-Brentano versus Gray-Zinc incidence. Here we can see that, let's say for Bragg-Brentano, we have 2 very strong peaks. These are related to the substrate. While when we do Gray-Zinc incidence, we remove these 2 peaks, but we get some more layers, some more information of the layers, and these are very strong peaks, which are actually hardly noticed by classical Bragg-Brentano measurements. Okay, then another application, which is also very, very important, is reflectometry. This is, let's say, if you study interfaces, this is the D2, or if you study heterostructure, this is also very important. Why? Because you can get information about the density of the layers, about their thickness, roughness, and some information about the interlayers. So actually, this is a reflection event, so it depends on the reflection coefficients of different layers as well as defects and densities. I mean, densities are actually related to reflectivity. And basically, what you need to have is a parallel beam, which is produced with the hybrid, with the low divergence, and then beam tunnel on the diffractor side. This is basically the collimator. If you want to analyze, I mean, this is a very good tool if you have a very thin layers. Because if you have a thick layer, then you need to have really high resolution setup, which we also have. But then you need to take care that you put hybrid on the primary side, and on the diffracted side you need to put triple axis monochromator. But I mean, this is basically what I'm trying to say here, that this is the technique which is meant less for thick films, but more for let's say very thin films, because you have very nice fringes. And it is very important that you align the sample very carefully, and this can be done on different cradles. So what you get with the change, basically what you do, you change omega and you change 2 theta, both at the same time, and then you measure the reflection, so at very small angle reflection is very high, and then when you increase them, you go down with the reflection, and you observe if the interface is very smooth, some fringes, and these fringes are related to actually the thickness, the density, the roughness of the film that you have. Plus, if you have, let's say, a heterostructure, there you have, let's say, one film is very thick, and one, let's say, one is like this, and then one is very thin. Yeah? And basically, with this thin, you get basically you have it goes pretty deep. But what you have a superposition of smooth fringes on fringes which are broad. Yeah. So basically, it can be very nicely applied to heterostructures with quite different thicknesses. If thicknesses are very comparable, then the modeling gets complicated. Okay. So as for sex, you can do amorphous, polycrystalline, and single crystalline samples. Roughness should be quite small. So if it's above, let's say, above approximately 3 nanometers, then it's getting hard to investigate these films. And you can analyze thicknesses between 0.1 nanometers, so really thin layers, up to 300. But actually, it's easier to investigate very thin layer as very thick layers. Now we arrive to actually the most important application which we can do. This is high resolution XRD. It's also the most difficult one, and it is meant for analysis of epitaxial layers. What we would like to do, we would like to determine the composition of the layer, what is its crystalline quality, not only for the layer but also for the substrate, what is the relaxation state of that layer, what is its thickness, whether the wafer is curved, what is the mist count, the main size, and so on. So first, what is epitaxial layer? Epitaxial layer is something that has a certain relationship with the substrate. So our layer has to have a certain relationship in in-plane and out-of-plane direction with respect to the substrate. So this is the in-plane direction, this is the out-plane direction. So in the in-plane, it has to be, let's say if this is 001 direction, then this is also, let's say 001. It can be also a different one, but the film should have only one direction with respect to the substrate. And this should be also valid for the in-plane orientation. So one in-plane orientation with respect to the substrate. Normally you get epitaxial layer in case they're somehow clamped to the substrate. So basically you need to have effect of the substrate on the film. Yeah? In this way you can actually grow material in oriented way. If this clamping does not occur, then we have a relaxed layer. And basically you have two options of clamping. It can be compressed, or the unit cell can be compressed or expanded. Yeah, so then you have different types of mismatches. Yeah? If the film is completely relaxed, then normally you grow your material in a polycrystalline way. You have also something in between. This is your so-called texture sample. So that's texture sample is a sample which grows in the same out-of-plane direction with respect to the substrate, but these kind of layers have random in-plane orientation. So basically you have cubes which all are oriented, let's say, in 001 direction with respect to the substrate, but then this in-plane is just random. Yeah? Okay, the setup that is required for this kind of measurement. So X-ray tube, then you have a mirror which is changing divergence state into the parallel beam. Then you have germanium crystals. These are 2 to 0 germanium crystals. This is a 4 bounce crystal, so actually your beam is bounced 4 times. 1, 2, 3, 4. And then you have really a light with very narrow distribution of wavelengths. And this can be then applied on your sample, and what you're getting out is exactly what is related to your sample. It's not related to your instrumental bordering. So in our configuration, we have like this. Yeah? We don't have 4 bounce crystals, but we have 2 bounce crystals. Actually, this there is a certain trade-off. Yeah. So if you have a configuration like this, you drop the intensity dramatically. Yeah? So actually, if you want to get anything out of your sample, you have to collect data the whole day. Yeah? But then it's a very high quality data. But we also do, let's say, powders for not very routine samples. For routine samples we have another diffractometer, but let's say for slightly better data processing. But then we decided for 2-bounce crystal because they have, let's say, for the system that we are looking at, a good relationship between the resolution and intensity. Yeah. So this kind of geometry is used, let's say, when you grow semiconductor materials on semiconductors. Yeah. Because this is really high-end epitaxy, or let's say, single crystal growth of materials on single crystals. But let's say we do oxides on oxides, we do oxides on silicon, and in these cases the broadening of peaks which are related to imperfection of crystals is bigger than the instrumental broadening. Yeah? So therefore it doesn't make sense to go to really high resolution measurements. But then what we have is a triple axis, which is again removing everything else than the signal related to the sample. Okay, so this is just one more slide which is actually used to convince someone that we need, let's say, high quality signals. So this is, let's say, blue is just a parallel beam from the mirror, and then red is 4-bounce hybrid. Yeah. So basically, this peak and this peak is K alpha 2, and they are also much broader than this one. Yeah. So actually, you can see then if you calculate out something from this, you're much more sure that this is sample related, as if you calculate something out from the blue one. Yeah. Okay. In the reciprocal space maps, we get different shapes of our peaks. So these shapes are, let's say, like this. Yeah, this is actually a circle, a sharp peak, and this means that your substrate or layer has a high quality. Yeah, no distortion at all. So normally we get this kind of peaks for substrate, but not always, even for substrate. Then we observed different broadenings. They can be in vertical or in horizontal direction. Yeah? If the broadening is observed in, let's say, in this direction, vertical, then this can be related to the nature of thin film. So basically, if you have a 3D lattice, then in the reciprocal space map, this 3D lattice can be represented just using a single point. Yeah. Then, if you have a 2D feature, then this 2D feature is represented with a rod in the reciprocal space. Since we are dealing with the thin films, these are not perfect 2D structures, so they have a certain thickness, and that implies that these rods are not really rods, but are elongated peaks. Yeah? The same can be obtained in case we have a certain despacing in the thickness of the film, so we get this kind of peaks. And then we have broadening also in a horizontal way. This can be done for structures with a certain mosaic spread. What is this? This is actually, you grow a material in let's say 0,01 direction, like this, and then this growth is not as perfect as it can be, so then this 0,01 direction is slightly inclined into different directions. Yeah? And this can be represented as this kind of broadening in the RSM. Plus, if you observe something similar on the substrate peak, this can be related to the curvature of the substrate. So let's say this is a full reciprocal space map. Actually, you have points which are related to the substrate, and you have points which are related to the thin film. So these are the so-called symmetrical scans, which are done in direction parallel to the surface. Yeah. In addition to that, you can have asymmetrical scans, which are these scans, left, right, and left to the symmetrical scans. So with these scans, you analyze planes which are inclined with respect to the substrate. So basically, with symmetrical scans, you can figure out what is the despacing. So this is the spacing in out of plane direction. Yeah? Here we have 00L spacing. Yeah? With the inclined surfaces, we can get information about spacing in out of plane direction and about the spacing in plane direction. So for the substrate and for the film. So we can say what is then the lateral dimension of the film and the substrate, yeah? And based on that we can calculate out the strain, yeah? of the film. Yeah? So this is actually very important. So here we have, let's say, a fully relaxed film. So you can see that actually it does not fit to the substrate, so it's just on top of it. And how can we observe that? So actually in the symmetrical scan you don't see any displacement in this direction. This is because you analyze material in this direction. But then if you connect a symmetrical peaks with the origin of the RSM, you observe that these two points are in the line, yeah? And that means that actually your film is relaxed. In case the films are fully strained, then if you draw a line, they are not on the line, but they are in the line which is perpendicular to the RMS. Yeah? Okay. And this is, let's say, just an example of one real RSM image. We have silicon substrate, we have a silicon germanium film. Based on this image you can calculate then the unit cell dimensions in different way. You can say whether it's relaxed or strained. And actually the good thing is that you have the software which enables you to get this information quite quickly out of it. There are certain tricks which needs to be applied. Actually, you have to figure out which points needs to be analyzed. So basically, normally we decide for points which are here, yeah, for these points. Yeah. Why this is so? Because at these conditions you can work at very high incidence angle, so very high omega value, in very small exit angle. So this is also called Gray-Sink exit analysis. In this case, what you have, so a beam has a certain width, and if you shine on your crystal at high angle, then you get a quite thinner signal which is going out. So this thinner sample is then better for the analysis of your sample. So here you see that by proper decision of peaks which are analyzed, you can further improve the resolution. Yeah? But nevertheless, these acquisition times are quite high. Let's say for this kind of image, you need let's say the whole night. Yeah? Okay, so these are scans like this. Yeah. So you change in a certain way omega and 2 theta values. These are the so-called 2-axis measurements. Let's say this is all classical omega 2 theta measurements, and in addition you can also do 2 theta measurements and omega measurements. So let's say for thin film community, what is quite often used is omega measurement. So this is this kind of measurement. This measurement is also called rocking curve. Yeah. This is done on, let's say here on this film and this substrate, and based on the rocking curve, you can calculate out what is the full width half max for, let's say, for your film and for your layer. And this is the value which is used to characterize the mosaic spread of your films. Yeah? So as I said, the broadening in this direction is described for mosaicity. Yeah? So basically, if you do scanning this way, you cannot describe mosaicity. Yeah? Broadening in mosaicity is described in this way, so you need to do rocking curve. Yeah? So okay, sometimes people are describing full width at half max from normal 2 theta theta scans. Yeah? But this is actually not done in thin film community. Yeah? In thin film community, they calculate these values out of rocking curves. Yeah? Okay, then we arrived to another application. So that was high resolution measurement. Then one also important application is texture. This is, let's say, done more for ceramics. Yeah. So what we do, also for thin films, but let's say we have some oriented ceramics with very, let's say, emphasized functional properties, and these properties are quite often described to texturing of samples, and this texturing can be then quite nicely analyzed with this application. So what we determine is distribution of orientation in the material. Yeah. And how can we do it? By changing phi and chi values at a specific 2 theta omega value. So we put a sample into the diffraction condition, and then we change phi and chi a little bit. Yeah. So this is it. Yeah. So this is a diffraction condition for one crystal plane, and then actually around this value we rotate the cradle for 360 degrees, and we change chi a little bit. Yeah. So we need a point focus geometry, and on the diffractor side we need a collimator and a detector in 0 G mode. Yeah. Or a linear detector. Yeah. Okay, this is, let's say, a typical pole figure. Yeah, this is for a specific set of planes. In the single crystalline material, what you would get is points. Yeah, but here we can see that we have a certain distribution of orientations. Yeah, that means that okay, the ceramics that we are having, let's say, is not perfectly, grains are not perfectly aligned. Yeah, but have some orientation. Yeah, but normally, if it would be randomly orientated, you wouldn't see. Actually, you would see the same intensity all around for 360 degrees. Okay, then another application is in-plane analysis. This is the so-called real in-plane, when you put the cradle completely into the out-of-plane geometry. So we analyze planes which are perpendicular to the surface. In this way you can get information about in-plane lattices. Basically you can get all this information also from RSM, but let's say sometimes this is even better, even more accurate. You can see what is the relaxation state of the potential layer, and you can get some more signal from the top layers. Let's say here is a example of a hard disk. So you have different materials, copper, chromium, and then amorphous material and substrate. And actually this is a symmetrical scan. So just basically, let's say, the Bragg-Brentano geometry. So what you can get, a very strong information about the substrate, amorphous background due to nickel phosphate, and some peaks which are not actually resolved, since these layers are very thin. But when you do in-plane analysis, what you can see is that with a certain configuration of omega and 2 theta values, we can get only information about really the uppermost layer. Yeah? So here you can see you have 3 peaks which are actually hindered in the amorphous peak. Yeah? Okay, and then the last application is 2D. It's actually more or less for show off. Yeah, I would say. Yeah? So actually, these are the so-called debye rings. This is what people used to analyze like 40 years ago, when they had normal old cameras, and then they had a film, and then they observed these rings, and from the rings they calculated out what is the spacing. And okay, if you have a polycrystalline material like this, yeah, then you get a diffraction in different orientations. Yeah, when you're in the diffraction conditions. Yeah. Then if you have a material which is, let's say, more coarse, and it's not completely well aligned with respect to the space that is used with your diffractometer, then you have points. Yeah, like here. Yeah, So actually what you're doing, you're changing this material, this pattern to this one. Yeah. But basically if you have a single crystalline material, then you would get only certain points. Yeah. This is also again just a more well-oriented polycrystalline material with respect to this one and this one. Yeah. So what you do, you just move the detector as you change 2 theta and 2 theta values, and then basically by doing that you can get this kind of debarbarates. And let's say nowadays you can already get articles which are just showing, okay, I prepare material in one way, I have a polycrystalline material, I prepare material in another way, I have a single crystalline material. And then they just presented one image of this, and then one image of this with just some points, and then this is a proof of the epitaxy. Yeah. Okay, so conclusions. So with the device that we have, you can do many different characterizations. So from loose powders to epitaxial thin films. We can also analyze some solid objects. Yeah, like let's say for industry. We can change this configuration quite quickly. Let's say optics can be changed within 5 minutes, while for let's say high temperature or low temperature stage we need like half an hour. I would say half an hour if you are experienced. And then you can choose different optics according to the quality that is needed. And actually, due to these changes, it is also possible that you can upgrade your system afterwards. Let's say, if there will be a need, we can go to 4-bounce crystal. Yeah, it's just a question of money that you have to buy one more of these solid pieces. Yeah. Okay. Maybe here I would like to put just to mention one more thing, that in addition to this diffractometer, we have one relatively new or old diffractometer. I don't know what. If something is 10 years old, I don't know whether it's old or new. And that diffractometer is actually used for routine powders analysis. So basically, what we do, we collect data from powders on the diffractometer D4. It's from Bruker. While we do, let's say, more profound powder analysis and thin films analysis on this analytical device. Yeah. So now maybe if you have some questions, I'll try to answer them, and maybe afterwards we can go on site and check the device. I can show you how it looks like.
Questions? I have one. You know, in ferroelectrics you have domains, and can you evaluate the size of the domains from the distributions?
Let's see. So domains.
Because they can act. I think they can act as.
They have different crystal orientations. Yeah. So basically, it should be possible. Yeah. It should be possible. Yeah.
And the size limitation is how much? Is nanometers?
Well, I mean, if you do RSM, then if you have time, if you have enough time, then basically you can analyze layers which are like just two layers, of something. So basically, like what I would say, 1 nanometer or even less. But then the acquisition time gets longer. Yeah. If you have, let's say, both ferroelectric material, I wouldn't see a problem to figure out the orientation. If you have a randomly orientated, then you have contributions for different orientations, and they basically would neglect this random orientation. But if it's both, then I think it's possible to say something, even with a quite simple diffractometer.
If I understood right, that you were talking about the different humidity, that it's possible also to check, but you don't have this.
No, we don't have this. I think in Kirka they have it, because they do these pharmaceutical things and they need to increase humidity. So it's I think it's nice also for you, for K&N ceramics.
I have one question. What is the lower limit for the mass of the sample? Let's say in
For
formal mass of the sample,
Okay.
in form of powder, let's say.
We can put powders on different holders. So for low quantity samples, we have silicon zero background holders. So basically, if you put one crystal, it might be enough. Yeah. Yeah. If you shine on this crystal long enough, then you can get some refraction out. Yeah. But yeah, it's always good to have a little bit of powders. But let's say for routine measurement, and if you want to do some, let's say, read field or size strain analysis, it's good to have 1 gram of powder. Yeah.
Somebody else? If no, thanks for really interesting presentation.
Yeah.
Okay.